This question tests your understanding of how the multidimensional scaling, MDS, algorithm works, specifically in Sklearn. I'm checking if you understand how MDS reduces data dimensions while considering important aspects like distance preservation and how the algorithm parameters affect the results. It's all about dimensionality reduction. This is what the MDS algorithm gives you after processing your data: a two-dimensional representation of your data. Think of it like taking a 3D object and creating a 2D shadow. It's a lower dimensional view of the original data. This is a critical measure of how well the MDS algorithm did. It tells me how similar the distances are between points in the 2D output compared to the original distances. A lower stress value means the 2D representation is a good approximation of the original data. Higher stress means it's a poorer approximation. It's like measuring the goodness of fit. This refers to a critical parameter in the MDS function. Means that I'm trying to preserve the exact distances between data points. Means I only care about keeping the order of distances, e.g., A is closer to B than C. Think of it as the level of precision you want. I'll explain multidimensional scaling, or MDS. It's a technique we use to reduce the number of dimensions in a dataset while trying to keep the distances between points as similar as possible. Imagine you have data points scattered in a 3D space, and you want to represent them on a flat 2D map. MDS helps you do that. Sklearn provides a convenient way to perform MDS. This statement is incorrect. MDS aims to preserve the original distances, but it's not always perfectly accurate, especially when reducing the number of dimensions. Think of it like trying to flatten a crumpled piece of paper. You can get it close, but you'll never get it perfectly flat. This is absolutely correct. The stress value is a number that measures how well the new, reduced dimension distances match the original distances. A lower stress means a better fit. The new distances are closer to the old ones. Setting metric equals true in MDS tells the algorithm that you're working with actual distances, like miles between cities. The algorithm will then try its best to preserve those distances in the lower dimension, but it doesn't guarantee perfect preservation. It will always try to come as close as possible. This is incorrect. _random_state is used to make the results reproducible. This means that if you run the MDS algorithm multiple times with the same _random_state, you'll get the same results each time, regardless of max_iter . It's like setting a seed for a random number generator. It ensures consistency. This quiz tests your understanding of multidimensional scaling, MDS, a technique used to reduce the dimensions of data while preserving distances between data points. We'll explore how MDS works and what parameters are important. This is the core question of the quiz, asking you to analyze the results of applying Sklearn's MDS to a distance matrix representing cities. The question assesses how well you understand the implications of different parameter choices and the interpretation of the results. This question sets up the context. It explains that you're dealing with geographical distances between cities and using MDS to reduce the data to two dimensions. The use of _random_state equals 42 emphasizes reproducibility. It helps to ensure that the results are consistent if you run the analysis multiple times. This statement presents the first option. The question is whether the distances between the cities in the 2D representation perfectly match the original distances. I will evaluate the validity of this claim later in the analysis. This option introduces the concept of stress in MDS. I need to determine if a lower stress value indeed implies a better fit to the original distances. This is another option to assess. Here, we analyze whether using metric equals true guarantees perfect distance preservation in the lower dimensional embedding produced by MDS. The final statement relates to the role of _random_state in the algorithm's behavior, specifically in relation to the max_iter parameter. I need to confirm whether this dependency is correct. This question tests your understanding of how Sklearn's multidimensional scaling, MDS, works, specifically when you're using it to shrink the number of dimensions in your data. It focuses on how well MDS preserves the original distances between data points after the dimension reduction. you'll be looking at the effects of different settings within the MDS function. This sets the scene. You're using MDS, a technique to reduce high-dimensional data to lower dimensions, in this case, 2 dimensions, on city distances. The n_ components equals 2 means we're aiming for a 2D map. random_state equals 42 ensures we get the same results each time we run this. Reproducibility is key. The question will ask you about various properties of the outcome of this process. This statement is about stress, a key measure in MDS. I'll explain. Stress quantifies how much the distances in your new 2D map differ from the original distances. A lower stress value is better because it means the new map better reflects the original distances between cities. Think of it like this. Lower stress means a more accurate map. Here, we're discussing the metric equals true parameter. When set to true, MDS tries its best to maintain the exact distances. However, this isn't always perfectly possible, especially when squeezing many dimensions down to just 2. Even with this setting, some distortion is unavoidable when reducing dimensionality. The random_state is for reproducibility. If I set it to a specific number, like 42 here, I'll always get the same results. This statement is incorrect because random_state will help in obtaining consistent results independent of the number of iterations. It helps ensure consistent results regardless of whether max_iter is defined. This is a quiz question testing your knowledge of multidimensional scaling, MDS, a technique used to reduce the dimensionality of data while trying to preserve the distances between data points. We'll focus on understanding how MDS works in Sklearn, a popular Python machine learning library. Let's dive in. Imagine you have a map showing cities and their distances. MDS helps you create a simplified 2D map, like a scatter plot, retaining as much as possible about the relative distances between cities from the original complex map. Sklearn's MDS is used with specific parameters. I'm reducing to 2 dimensions. n_components equals 2 and I'm using a random seed. random_state equals 42 for repeatable results. The stress value is like a measure of how well the simplified 2D map matches the original distances. A lower stress value means the distances on the new map are closer to the actual distances. A higher value means they are less accurate. It's how I quantify the goodness of fit. Lower is better. The random_state parameter is like setting a seed for a random number generator. I use it to make sure I get the same results each time I run the algorithm. If I don't, the algorithm's internal randomness might give me slightly different results. Think of it as ensuring reproducibility, the same starting point each time. The metric equals true parameter tells the MDS algorithm to try to preserve the actual distances between points precisely. It's the standard way to use MDS, but remember, it can't perfectly preserve them when reducing the dimensions. There will always be some error, especially when squeezing many dimensions into just 2. This statement claims that the distances on my simplified 2D map will perfectly match the original distances. That's usually impossible. When reducing dimensions, some distortion is inevitable. It's just a simplified representation. This refers to the numerical result indicating how well the MDS algorithm did in preserving distances. It's a key measure of the quality of my dimensionality reduction. A lower number indicates a better fit between the original distances and the distances in the simplified 2D representation. This is the final result of the MDS algorithm, a 2-dimensional representation of my data, where each point represents a city and the distances between points, hopefully, somewhat reflect the actual geographical distances. This is the new, simplified map. This is the core of the process. MDS is the algorithm. I am using it with 2 parameters. n_components equals 2 specifies that I want to reduce the data to 2 dimensions, and random_state equals 42 sets a seed for reproducibility. This is the starting point, a table, or matrix, showing the distances between all pairs of cities. That's my original, potentially complex, map. This question sets up the scenario. We're using a popular machine learning library, Sklearn, and its multidimensional scaling, MDS, tool to shrink a dataset. The dataset shows how far apart different cities are. I'll focus on understanding how well MDS does this and what factors affect its performance. The stress value is key here. It measures how much the distances after *MDS differ from the original distances. A lower stress means the MDS algorithm did a better job of keeping the distances similar to what they originally were. Think of it like this. If I'm trying to draw a map of cities preserving their real-world distances, a low stress means my map is quite accurate. A high stress indicates my map is a pretty bad representation of the actual distances. This statement is a bit tricky. Setting in MDS tells the algorithm to try its best to keep the exact distances the same, even when we squish the data from many dimensions down to only 2. However, it doesn't guarantee perfect preservation. Some distortion is almost always inevitable when reducing dimensionality. It's like trying to flatten a perfectly round ball. You can't do it without some stretching or squeezing. The randomstate parameter is like setting a seed for a random number generator. It's used to make sure we get the same results each time we run the algorithm. It's particularly important with iterative methods, algorithms that repeat steps. The statement says it only matters if the maxiter, maximum number of iterations, isn't set. That's not entirely true. Randomstate impacts reproducibility regardless of maxiter setting. It's always good practice to set it for reproducible results. I'm using Sklearn's multidimensional scaling, MDS, a technique that helps me shrink high-dimensional data into fewer dimensions while trying to preserve the distances between data points. Think of it like flattening a crumpled map. I'm trying to make it smaller but still keep the cities roughly in their correct relative positions. MDS stands for multidimensional scaling. The question tests my understanding of how MDS works when I use it on real-world data, specifically distances between cities. I'm given a bunch of distances, like the distance between New York and Los Angeles, and I'm using MDS to make a 2D map, where each city is a dot on a plane. My input is a table showing the distances between all pairs of cities. For example, one entry might say the distance between New York and Los Angeles is 2,445 miles. MDS takes this matrix of distances as its starting point. The output of MDS is a 2D representation of the cities, meaning each city has an x and y coordinate on a plane. This essentially gives me a simple map of the cities based on their original distances. After MDS creates the 2D map, the stress value tells me how good of a job MDS did. A lower stress means the distances in my simplified 2D map are closer to the actual distances in my initial distance matrix. A small stress means a good map. A large stress means a less accurate map. It's a measure of how much distortion was introduced during the dimensionality reduction.